Good morning everybody. Friends, we are back here again with this rate processes. So, we were in reaction dynamics, and we started with this collision processes, and we discussed many other aspects, and in our last lecture we have taken up this mechanism, like one is Harpoon mechanism, and we also discussed this rebound dynamics. Now, as a as a recapitulation, now Harpoon mechanism, what is this Harpoon mechanism? Now, this reaction has got a large cross section, okay, very large cross section, and generally forward scattered products are obtained, forward scattered products, and in the translation mode low energy is released, and generally your product is in internally excited state. So, product in the internally excited form, excited state, okay. And it is in this case what happens that for this Harpoon mechanism, fairly heavy reactants, okay, plucks the light atom from the other reactant, okay, and basically the remaining part is acting as if it is a spectator. It cannot do anything, okay. So, and reaction occurs, okay. So, basically the reaction is like I have given example of K plus I2 or maybe K plus Br2 giving rise to Ki plus I2, sorry, Ki plus I. So, it plucks iodine from this I2, okay. And this is one thing I discussed. Next we talked about this rebound dynamics, and we have taken the example of K plus CH3I giving rise to Ki plus CH3, okay. And in this case, in this particular case, cross section is small. So, cross section small, and back scattering, we get back scattered product. So, back scattering, and the energy is mostly in translation form, okay. So, that we talked about. You can have other examples like fluorine plus hydrogen giving rise to HF plus H, where HF is in the vibrationally excited state. Next, we will start with controlling reagents, okay. Controlling reagents and product characterization. Okay. Now how to select, means how to select that. So, in the molecular beam you can there is option to set the velocity, select the velocity. So, selection of velocity. So, the thing is selection of velocity in the molecular beam. Okay. So, basically here you see that your two molecular beams, they are intersecting over here, okay, and they are at 90-degree angle perpendicular, and the detector is oriented somewhere in between, so it can move in this way. So, so angle as a function of angle it can change, so that the detector can detect the product in various angles. Okay. Now, the question is, do you really have to keep the two beams at perpendicular direction at an angle of 90 degree always? So, the thing is that that we can change actually. Okay. Now, there are means. Now, the way is like that. One thing is that how to select the velocity. Okay. I mean, this selection of velocity may be, it is not the absolute velocity, but it may be a relative velocity. Relative velocity as well. Relative velocity as well. Now, how to select the speed, I mean velocity. Now, this can be achieved by chopper, like here, like the beam shutter, you can have a chopper, okay, like chopper blade, like fan blade, okay. So, you can chop certain speeds by that, okay. So, it is moving, this chopper is moving this way, so it selects specific velocities, okay, like depending on speed like the chopper can be like this. It is a part, I am showing just a part of that, that so when molecular beam is perpendicularly falling on this portion is, there is no block, I mean it is open, so molecules can pass through. Next, when say this is rotating this way, so next instant maybe for some time, suppose it has got the speed, some speed, so that I mean, and your molecular beam somewhere over here, so this will continue to keep keep the molecular beam to go to the other side of this page as long as this block is coming over here, okay. So this molecular beam will be on for this much of time, I mean the time required for this part to come to here, okay. So it will remain on and then off for this much of time, okay. So depending on speed, the molecules which are able to come here can pass through, and those which are not able to come to this plane of your paper will not be able to pass to the other side of the paper. So slower moving molecules you can select, I mean slower moving molecules you can stop, and you can allow only faster moving, or vice versa, depending on your necessity, whether you can, if you are and rotating this this chopper at some different speed, at some lower speed, then it will allow lower speed to pass through. So this way you can select. So that is one mechanism. So it is a kind of like this is, although it is beam is completely blocked by this, but if you can arrange, means if you can replace this with a like this chopper, you can select different speeds, okay. That is one thing, okay. Next is, I mean, use of a chopper, chopper, okay. Maybe if you change the pressure difference, okay, pressure difference between the source and the target, okay, so that will also change the velocity. So controlling the pressure, okay. And third is introduction of seed. Introduction of seed, okay, that is it mixed with some seed beam, okay. You can change it, I mean, so there is a collision between the seed molecules with your reactant, and then the velocity may change, okay. Another option is that changing of the relative velocity. So changing of the relative velocity, that is changing the relative velocity. You can do it. So like if you can change the angle between this beam, so this is one path, and suppose this next one is oriented at an angle which is not exactly 90 degree, maybe this way, okay. So that means in that case, suppose this is your A, okay, and and say this is your originally this was your B. So your relative speed is this C relative. In other case, say A is remaining like this, like here, okay, and your relative speed is now has changed, like somewhere here. Say if you keep the length fixed, so this is your C prime relative, okay. So this is your A, and say this is your B, okay. So so you can change the relative speed by changing the angle between the two beams, that is the intersection angle, the angle of intersection, that is the angle originally the angle was like 90 degree. Originally the angle was like 90 degree as here 90 degree, but you can change the angle, okay. You can change the angle, okay. So that will change the relative velocity, okay. Now next is the question of selection of internal states, okay. So selection of internal states. Internal states means various quantum states, okay. So you can do that by applying inhomogeneous fields, that is inhomogeneous electric fields. The thing is that the molecule, in that case, molecules, I mean your reacting molecules, the requirement is that your molecules should be polar, that is dipole moment mu should not be equal to 0. Okay. So, dipole moment that should have permanent dipole moment. Okay. And what you do is that, so you have got say plus or minus plate over here. Okay. So, these two plates are oppositely charged, and so what you do is basically say this is your minus plate, say this is your plus plate. Okay. So, this is, so this from this side your molecular beam is coming, molecular beam containing polar molecules. Okay. So, what will happen that this cold molecular beam, they will tend to be deflected this way. Okay. So, if we view, this is a side view, if we view from the other side, it will be something like, it is like hexagonal alternate plus minus. Okay. Plus minus alternate, minus, this is plus, this is minus, this is plus, this is minus, this is plus. So, molecules will pass through this inhomogeneous electric field. So, you see that it is not homogeneously changing from here, if you go from here to here it is plus, again it is minus. Okay. So, and again it is plus minus. So, it is changing constantly with position. Okay. So, it is changing constantly with position. So, and depending on the internal state of the molecules, internal state means whether it is like different J state, that is rotational states. Okay. So, you can select. So, basically the velocity with which, so what you have to do, you have to focus, like right. So, focus say somewhere over here. Okay. So, these molecules will be will be attracted, and then again it will go this way. So, basically if the field is not there, they will pass in a linear fashion. The moment it is you apply electric field, it is bulging out. So, it becomes like a concaved kind of convex kind of thing, and then ultimately again it will focus over here. Now, this focusing will depend, means where it will focus, it will depend on the velocity, that is this velocity. So, focusing, so it will depend on velocity, and also it will depend on the electric field strength, and magnitude of mu, and actually depends on mu dot E. Okay. Basically mu dot E means mu E cos theta. So, component of dipole moment along the field. Okay. So, it is a dot product. So, component of dipole moment along the field, it will depend. Okay. And separation, I mean energy change as a result of this this interaction with dipole moment and E is given by mu dot E. Okay. So, originally energetically degenerate levels are now not degenerate as a result of this interaction. Because of this interaction, they will no longer remain degenerate. So, there will be some separation of energy levels. So, energy levels are, degeneracy is lifted depending on its depending on the interaction of your dipole moment with E. Okay. Now, then the thing is that next is you can select. So, one option is your inhomogeneous electric field. Using inhomogeneous electric field you can select internal states. Okay. Now, you can do that by also by laser excitation. There is another means which is called the laser excitation method. Okay. So, internal states can be selected. Okay. Can be selected with the help of laser excitation. And high number density, that is high population, is sometime high population density of the excited species is sometime difficult, okay, in cross molecular beam experiments. So, in that case although we can select, but depending on laser intensity and also frequency, but it is possible internal states can be selected by means of by using laser excitation. Okay. Next is how to control the reagent orientation. So, controlling the reagent orientation, controlling reagent orientation. Okay. Now, another option is although I talked about this inhomogeneous electric field, where you can, depending on the interaction between your field and between the dipole and the field, you can select the different velocities or different internally excited states. Next is you can apply a very weak electric field. Okay. So, weak electric field like say, okay, there is a weak electric field, say, in between these two parallel plates, and a polar molecule will be oriented in a definite fashion. Okay. And it should not be very strong field, it is a weak electric field. So, polar molecules will be oriented appropriately. So, by this way you can have the orientation of the reagent. Another important thing is that because whenever you do laser excitation, so laser is basically strong electric field. So, the moment this electric field is passing through your reaction mixture, the moment it is passing through, what is happening, that and also laser is a polarized source of radiation. So, polarized means its electric vector has got a definite definite plane. Okay. So, this electric vector is oscillating in a definite plane. So, the moment it is passing through your mixture, gas mixture, because we are dealing with gaseous reaction and molecular beams. So, the polar molecules will be oriented means there is a great chance of those molecules getting oriented with respect to the electric field vector of your laser source. So, this way there is there is a chance of orientation. So, if you use a weak electric field, then you can so for by weak electric field you can get oriented species. The thing is that only important point is that for polar molecules, of course, for polar molecules, and this orientation is because of the Stark effect. So, and this is because of Stark effect. So, first order Stark effect. Okay, and this average angle between the field and the dipole moment is basically, you know, mu dot E cosine theta average, which is you know, which goes as like this. So Km divided by J into J plus 1, this way. Okay. So this way you can select, you know, select rotational states. Okay, you know, applying your first order Stark effect. Okay, you can select different different states. Okay, depending on how much electric field you are applying. Okay, so depending on electric field, this perturbation is coming accordingly. So therefore, you are selectively, you know, generating the perturbed state. Okay. Next is we'll have a you know, an apparatus which is taken from Journal of Chemical Physics 2001 edition, volume 115, where this apparatus you know, gives you the idea of how to, you know, do this collision experiments. Okay, so here you see that you know, it is a reaction between OH and carbon monoxide. Okay, so means it is a collision between OH and carbon monoxide. So oriented OH. Okay, now you see here you have got H2 and argon, they are mixed, and then it is passed through a high electric field, electric discharge, so that this OH is generated, and then this OH through a skimmer and is passed through this, you know, hexagonally oriented plates, alternatively plus minus this way. So it basically is a selector. Okay, it is a selector, and so it generates one partner, and of course it is state selected partner. Okay, and then you have got another partner. Okay, over here. Okay, it is also a pulsed valve, and then it's a skimmer, and there you have got two beams, and laser beam is here, and this is an orienting field you are applying. Okay, so what is happening, that you are measuring here the light induced fluorescence from your products. Okay, and there is a photomultiplier tube which detects the light induced fluorescence with corresponding optics is here, corresponding optical arrangement, so which detects the light induced fluorescence, and laser beam which you know, excites the sample, and then you accordingly get the laser induced fluorescence. Okay, so so basically it is a typical apparatus by which you can study. So it is a schematic, and it is taken from Chemical Physics, Journal of Chemical Physics. So it is an example of means how to study, and using of course the laser induced fluorescence as the detection technique. Okay, next we will move on to you know, is there any stereochemistry? Okay, that is whether some specific orientation is important for a reaction to take place. So for this, let us take one example, that rubidium plus CH3I giving rise to rubidium iodide plus CH3. Okay. Now the point is that you have got the point is here that you have got your CH3 like this, three hydrogen and one iodine, and you have got say rubidium which is coming say from this way, okay, and you want to know whether you are getting any RBI, okay, in the backward scattered direction, okay. So, to see whether signal when iodine end of CH3I is pointing towards rubidium beam, okay, that is important to know. That means look for RBI in the back scattered direction, okay. So, that is in this direction, okay. So, it is the back scattered direction, okay. So, so basically so if you measure that, then it should be giving you the idea that whether this geometry or the other geometry is important or not, okay. And whether there is barrier, I mean if it is approaching from this side, whether this you are getting your product or it is approaching from this side, okay. So, whether is there any means the reaction faces any barrier with respect to the angle at which it is attacking your reactant, okay. So, angle of attack is important. So, angle of attack means this is your line. So, maybe if it is coming this way, so maybe this is your angle of attack, okay. So, whether your backscattered product is very much dependent on the or the extent of your product formation is dependent on the angle, okay. So, if you want to know more on that, details on that, you can go through this Levine's text, okay. So, that is the basic idea, that maybe this, if it is attacking from this side or maybe from this side or maybe this side. So, amount of backscattered product you are getting is more or less. So, that will give you the idea, okay. So, and not all reactions display strong steric effect, because if it is approaching this side, so it cannot access this iodine. So, there is some steric factor, okay. So, the reactions which proceed without any barrier on the potential energy surface are not generally showing strong steric effect, okay. Next is if we would like to so here we have given you the idea of the steric factor and also told that if it is barrierless, then steric factor is less. Next is product states. Product states, okay. So, we would like to, we may need to measure populations of various rotational vibrational state, vibration states, that is characterized by J and V numbers, okay, of course in the products, and this provides information on the state resolved cross section, means which cross section of specific state resolved reactions. Okay, which states are more, having more cross section than the other. Okay, and that is quantified by P V prime J primed, which goes as sigma V primed J prime divided by sigma, where cross section is the sigma. So this sigma is the total cross section. It is provided it is known, we can find out this probability factor. Okay. Now, if the velocities are not particularly selected, but if the velocities are thermalized, I mean they are just thermalized, then the population provide information on the state resolved reaction rate constants. Okay, and the population provides the nature, information on the nature of the potential energy surface. Okay, so next is for the measurement. Okay, this molecular beam, since molecular beams, so it is giving you a platform of collision free environment. So platform for collision free environments. So that means there is no scrambling of internal states by energy transfer. Okay, that's one good advantage of molecular beam. Okay, but it is very difficult, to probe into difficult to probe the populations of the internal states. Internal states from cross molecular beam experiment. Okay, so it is very difficult to to find out this thing. So there requires other techniques by which maybe you should be able to find out this internal state population. So other methods are like one is infrared chemiluminescence. So luminescence as a result of chemical reaction. Okay, luminescence as a result of chemical reactions. Okay. So there are plenty of examples you will be finding in any standard physical chemistry text, like luminol. Okay. So if you react with H2O2, so it luminous. Okay. So it is a cyclic hydrazide, so it luminous. So and it is in solution. Okay. Now in gas phase reaction, like H plus Cl2 giving rise to giving rise to HCl B primed J primed, okay, plus Cl. Okay. So, this is your rotationally and vibrationally both excited, both rotationally and vibrationally excited system, okay, and it emits in the IR region, okay. So, it emits in the IR region. So, basically what is happening, that your hydrogen atoms, these are generated, these are generated by electric discharge, and because of this collision, because of this reaction, HCl is generated, gas phase HCl is generated in the rho vibrationally excited state, rotation, vibration both way excited in both sense. So, rho vibrationally excited, meaning rotationally plus vibrationally excited, rotationally and vibrationally excited, and it luminous. Okay. So, and if you can record the emission spectra as a function of frequency or as a function of lambda wavelength, you can indeed find out the population, that is population of the internal states, population of various V and J states. Okay. So, in this case what we have to do, that low pressure, in low pressure case, so like about 10 to the power minus 2 Pascal pressure, and which is low pressure will ensure that that mean free path is of the order of, which will ensure the mean free path of the mean free path of the process is of the order of vessel length, okay, okay, and HCl, what is happening, that this excited, this is, you can write as HCl star, okay. So, HCl hits the wall, sticks, and then it is deactivated before any secondary collision, okay. So, and IR emission, you have to record in IR emission spectrometer, okay. So, this is one way. So, you have to ensure that low enough pressure is there, so that this mean free path is about the vessel size, HCl hits the wall and then sticks and then deactivated before any secondary collision. Deactivated means this, it is emitting IR photons, okay. So, the thing is that it looks like an interesting piece of experiment, but the problem is that although in this case it is a nice example that you are getting IR emission, which means when plotted, this IR emission, which when plotted as a function of emission intensity as a function of lambda, will get you important information on the population of various levels. But the problem is, limitation is that not all products, I mean like this, are IR emitters, and of course they should be very strong IR emitter, otherwise it will be a problem, because if it emits but very weakly, then this will be of not that usage. So in this case limitation is like limitation of this infrared IR chemiluminescence method. To look into your internal state population. So it is limitation is like you need strongly emitting species in IR. Okay. Regarding status, the status of the ground state, not possible. So we do not get any information about the ground state. So this is another another problem. Okay, and first is the species should be strongly emitting in the IR. Otherwise infrared luminescence detector, I mean detector is it will not be very useful. So you need a infrared detector and your species should be strongly emitting in IR. But the problem is, since it is emitting from some excited raw vibrational state, so raw vibrational excited state, so you do not get any information about the population of your ground state. So what is happening to the ground state, it is difficult to know on that. Positive points, that one is limitation is a negative is negative points. So positive points, it is relatively universal. It is a universal method. Okay. Next is IR emission can be detected by time resolved FTIR techniques. Okay. So by means of FTIR, time resolved FTIR method, one can detect those IR photons. And it is very sensitive method. Okay. So nowadays this FTIR technique has been employed. Okay. So so positive, of course it is very, it's a very positive thing that that this method at least give you, although not for all reactants you can get information about this various levels like vibrationally and rotationally excited levels, that is the population on that, but still for some reactions like the reaction I am using over here, like H plus Cl2 giving rise to HCl in the raw vibrationally excited level, and HCl which is formed in the raw vibrationally excited level gives rise to infrared photon, and that gives you information on the population of these various levels. Okay. So that's why in that respect it is a successful thing that using infrared chemiluminescence, that is luminescence as a result of chemical reaction, you can find out the information of the various information of the population of various levels. Although it is limited, limited means like HF, HCl, these are useful. There are limited number of infrared emitters. Okay, and of course ground state information, it is not possible, because we are probing the upper level. So from upper level to lower level it is coming. Okay, and because of this luminescence, we can think of, we can calculate the population, whether the upper level, how much it is populated. You can find out. Okay, so as a function of wavelength. Okay, as a function of wavelength, if we can record the luminescence spectra, we can get information, means which one is more populated, which one is less populated. Higher level, which higher level is more populated, whether this higher level or that higher level is more populated. If this higher level is more populated, so chemiluminescence from this level will be more intense, is intensified compared to maybe this level. So from that, from the intensity distribution, you can get the idea of the population of this level. Okay, so so that is one important technique, infrared chemiluminescence. We can probe the internal state population. Okay, although from cross molecular beam experiments, it is difficult to find out, but from this method we can find out. Okay, so that's one method. Another method is laser induced fluorescence method. Okay, so another method which is used is LIF, laser induced fluorescence. Laser induced fluorescence to probe into the internal state population, for looking into internal population of internal states. So that we will take up in the next piece of lecture. So before we conclude today's talk, let us have a quick recap that reagent state selection in molecular beam we have talked about, and in this case by using chopper controlling the pressure, source pressure, and also introduction of seed can help in selecting velocity of the reactants. And regarding relative speed, relative velocity, you can change the angle between your two crossed beams, so that you can change. So you can change C relative, and you can internal state you can select by introduction of the inhomogeneous magnetic electric field. Generally there are 6 alternatively oriented, hexagonally oriented plus minus poles, and by means of laser excitation you can also select certain internal states. Okay, by the use of your first order Stark effect, you can also choose specific rotationally excited level. Now I have given an example of a typical example of a typical apparatus by which you can study collisions. Okay, and stereochemistry is an important factor for this reaction. In certain cases, barrier is very much dependent on the angle of collision. Okay, and looking into the backscattered product, you can see whether this process is having large barrier or low barrier, and generally when it is low barrier, then steric factor does not play that much of important role. And to look into the internal state population, we have discussed in short in that how you can measure the internal state population. That method is infrared, looking into the infrared chemiluminescence. So that will help in, that will give you idea on the population of the upper state rather than the lower state, that is the ground state. Okay. So that's all for today. So in the next piece of lecture we will start with a technique which is called the laser induced fluorescence technique. So till then, have nice time. Thank you.